Hi, and welcome to Unit 25. In this unit, we're going to talk about a very important effect called the Doppler effect. This is a phenomenon that I'm sure 100% that everybody is familiar with it. And this applies to any kind of waves. It doesn't have to be a sound wave. I mean, it doesn't have to be electromagnetic wave, which is light, really. It can also work with sound, and that's why I'm saying it's something that I'm sure people are they know about it. It's because you experience it in terms of sound. Let me explain. If you are standing, it doesn't matter where, okay, and you hear the siren of an emergency vehicle, whether the police, whether the fire department, whether the ambulance, you could tell if that vehicle is closing on you, coming closer and closer, or receding from you, moving away from you, just by the way that the sound comes to your ears. Okay, we have an intuitive notion of what the sound is, and then when the waves are compressed, the pitch is higher, so we know that that vehicle is coming closer and closer to us. We don't really need to see which way it's coming from. We know it's closing on us. Now, if the vehicle is moving away from us, the sounds, the wavelengths are getting longer and longer, which means that the pitch, the sound, the frequency is getting lower and lower. In which case, in this case, we can tell that that vehicle is moving away from us. We're here, and the vehicle is moving away from us. The distance between us and that vehicle is increasing. Why is this important? Because it's critical for determining how fast objects are moving in the sky. So for the stuff that is far away, okay, for the things that are nearby, we can check the angular displacement. Let's say if it was here, a month later it moved in here, so we have that angle that it has moved in a given period of time, and then we have distance over time, and that gives me the speed, albeit I really need to know how far that object is from us. So that's a technique of finding the velocity. But for far away objects, they're too far for us to determine that they have budged in space. So we're not going to find an angular displacement. So in that case, we're going to look at the spectrum of that object and see. Let's say we know a given spectrum. We know, for example, how hydrogen lines line up in the spectrum. There is one line in here, there is another one in here, there is a third one in here, and there is a fourth one in here. You come tomorrow and you see the entire spectrum is shifted toward the blue. Anytime, it doesn't have to be tomorrow. I'm sorry, I just said. So you look at the spectrum and you see it's the same spectrum, it's hydrogen. But instead of finding this ray here, we find it here. Instead of finding this beam here, we find it here. Everything is closer to the blue than what it should be. Then in this case, we know that the frequency is getting higher and higher. So that star or that galaxy is moving towards us. If, on the other hand, the spectrum of hydrogen, let's keep the hydrogen as an example, the entire spectrum is actually shifted toward the red. I mean, the blue is still blue, but it's the value of the wavelength is slightly longer than what it is. So it's different shade of blue, if you wish. The red is red. It did not change color, but it's a different shade of red that is closer to a longer wavelength. The violet is violet. Probably it has shifted so much as it becomes a blue. Then that thing is moving super fast away from us. Or it has shifted so much that the entire spectrum is not in the visible range. It's in the infrared range or the microwave range, so we can't see it. And that's the purpose of the James Webb, by the way. The James Webb was invented to detect the relic light from the early universe that is moving so fast compared to where we are right now that we will not be able to see galaxies. I mean, galaxies normally are white because they have all colors, but we would not be able to see them with an optical device, with a telescope, for example, or with the Hubble telescope, which has a range in the visible range. But with the James Webb, is sensitive to the infrared and the microwave. It would see those objects. So all the images that you see of the early universe from the James Webb, you cannot really see them with the naked eye. They're computer-enhanced images to enable us to see them if we were to see them. We can see them. But if we were to see them with our own eyes, that's how they look like. okay, shifted toward the visible range. The actual light itself is in the infrared and the microwave, okay? So let's get into the idea first. In here, we're going to describe the Doppler effect and how it depends on the direction of motion. Calculate the Doppler shift from a velocity and vice versa. Describe the Doppler effect that arises from rotation and internal motion of an object. The sun, for example, spins on its own axis. At times, part of the sun is coming towards us because it's spinning this way. And at the same time, other parts of the sun are moving away from us. So we can determine the rotation of objects that way. You don't really have to find the objects moving in or out. The same object, you can find how fast it's spinning or how fast it's rotating around the center points. Again, if you're standing in here and the emergency vehicle is coming towards you, the wave fronts are compressed because here is the deal. The source sends a wave front and moves towards it and sends the next one. So the separation between each two wave fronts is shorter than what it would be if the vehicle is standing still. Sends the first wave front and then waits a period of time and sends the second wave front. So the wave fronts are separated by a given length, that is the wavelength. But if the wave vehicle is moving toward in the same direction as the wave is moving, then it sends the wave front and then moves. So the next time it sends the next wave front, the separation between them is shorter. So the waves appear to have shorter wavelength. And remember that the wavelength times the frequency is a constant at the speed of light. Then in this case, the frequency appears to be higher. On the opposite side, if the vehicle is moving away from us, here is the deal. If the vehicle, for example, there is me, and here is the vehicle, okay, sends a wave. So the wave front will hit me, and then if it's still sitting still, the next wave front will hit me, and it will have a separation between each two wave fronts being the distance between the crests. But now, it's moving away. So it sends wave front and then moves away and sends the next wave front. So the distance between two wave fronts as it hits my ear, in this case, is going to appear with longer wavelength. And again, lambda times frequency, the wavelength is lambda, Greek letter lambda, times the frequency is the speed of light. So for me, the way I interpret it is that lambda has increased, the frequency has went down. So the pitch is of a lower tone, okay? So I can tell that this vehicle is moving away. So the wavelengths are stretched, whereas in this case, they are compressed, okay? And that's how police officers basically detect your speed. They use actually a radar gun that uses either sound or for light is going to be very difficult to find because the speeds are too low compared to the speed of light. But sound is perfect, okay? It's still too low compared to the speed of sound. Sends a wave, the wave bounces back based on the shift in frequency as detected by the radar. It will tell you how fast the car is moving, whether it's moving towards the vehicle, the police officer, or away from the police officer, okay? So it's that shift that really matters, the difference in wavelength. How much has it stretched or how much has it compressed compared to its original thing? That's the shift. The shift is the difference in this case. That tells me how fast the object is. So, again, that works with light. And for relatively low speeds, basically 10% or less than the speed of light, this formula works beautiful, okay? So basically the difference in wavelength, that's the wave shift, that's the wavelength shift, the shift in wavelength, divided by the actual wavelength as measured in the laboratory. For example, for the case of police officer, that wavelength is fixed. That is the device wavelength. It knows exactly what that wave value is. The wavelength that reflects and hits back the device is measured. The device automatically calculates the difference in these two wavelengths, divided by the actual wavelengths times, in the case of light, the speed of light. In the case of sound, it's the speed of sound. That gives you the relative velocity with which that object is either moving away or moving towards. If this number is positive, if the new wavelength is bigger than the old wavelength, then in this case, it's moving away. The wavelengths are getting stretched it's moving away. If the difference, delta, by the way, is the Greek letter for that we usually use for difference, the shift. So if delta lambda is negative, that means it's being compressed. The new wavelength is less than what the actual one is. So the new minus the old is a negative number. That means it's actually going to be blue shifted. That means it's going to move towards us. That's coming towards us, okay? So that's basically the distinction in the two. And again, you can clearly see in this schematic, the light source in this case sends waves, okay, and moves away and sends another one and so on and so forth. So the first wavelength is supposed to be on this side red, shifted. It's not necessarily a red color. It's a red shifted. That means the new wavelengths are longer. Whereas if you are in the front of it, it appears blue shifted. That means it's going toward the blue. It doesn't mean that the color has changed to a blue. It means that it's actually the wavelength is slightly smaller than what it was before, depending on how fast this thing is moving. It could change color if it is moving that fast, okay? It could start with a red color and then all of a sudden it appears blue. If it is moving that fast, but it needs to really be moving tremendously high speeds, okay? And again, you can see as the source is sending waves and moving in the same direction, the wavelengths are shifted more and more toward a shorter wavelength, higher frequencies, or longer wavelength, meaning smaller frequencies, less frequencies, okay? In other directions, it depends really. It's because the velocity is a vector, so you really have to use somehow the triangle formula for it. For example, specifically on this direction, there should be no shift in the perpendicular direction. So if an object is moving this way, sideways by you, I'm trying to make a 90-degree angle in here. So if it's moving at a 90-degree angle, for you, you're not going to see a shift because it's not neither coming to you or moving away from you. So in this case, there is no shift, okay? But if it's coming at any angle or moving away at any angle, then there is a shift that depends on the triangle, basically, relationship that you are looking at. So that's the basic formula for finding the shift in here. Okay, that we use. There is another formula that use the letter Z and its relative ratio and all of that. We're not going to get into it right now. We're probably going to discuss it down the road toward the end of the this class. Anyway, so again, I mentioned that fact, for example, for the sun, while it's spinning around its axis here, and the side that is moving sideways toward the Earth. It's not moving toward the Earth or away from Earth. It's moving at a 90-degree angle, either this direction or that direction. There is no motion towards or away. So there is no relative velocity. So the delta lambda is exactly 0. So the wavelength is exactly how it's supposed to be. Whereas this portion is coming towards us. It's moving towards the Earth. So this will be a blue shifted. The wavelengths are compressed. Whereas this one is moving away from us. It's the same object rotating, okay? Spinning on its own axis. And then in this case, it's going to be a red shifted. And again, the word in here, shift, doesn't mean that it's actually changed color. It means that it has moved away. It could be that it changes color, but that requires tremendous rotational speeds that probably will tear apart the object that you're looking at, okay? So again, this is just a description of this graphic. The fact that we can use, actually, this is also a very powerful technique trying to find the exoplanets or even binary stars, because you can look at the star, for example, as it spins around the central point, and based on the shift in the wavelength. So if you were to, for example, determine calcium, for example, a specific wavelength of calcium that is actually shifted toward this side of the red, or the blue, I'm sorry, and then this side of the red. And if you can determine how often this is changing between this side and that side, again, it's not changing colors. It's just slightly one side of what it's supposed to be and slightly the other way around of what it's supposed to be. And if this shift is symmetrical from the side, you can tell that this is going in a circular motion. If this this shifting back and forth is not symmetrical, asymmetrical, in a sense, it shifts toward the red, for example, some, and it shifts toward the blue more, then in this case, I know that it gets very close from the star. It moves from the central point. It doesn't matter what that is. If there is a black hole, or it doesn't matter what we are looking at in the center. So it's going to move fast, and then it slows down. So we know that their path is actually not circular, but rather it's elliptical. And we can even determine the eccentricity or the eccentricity of the orbit. So there's a lot of information that you can tell from the Doppler effect. Thank you.